I'm finally ready. So what's the point of these power series? So a power series now takes an infinite series and introduces a variable. And we said that that makes this like what? What does this make this kind of like? A polynomial, but that has an infinite number of terms, right? And so then, so we can analyze this series for many different values of x. And the point is, or what we're thinking about is then for what values of x will that converge and what values of x will it not converge, right? So if you look at this, we saw that the ratio test is going to help us determine that, right? So we're going to have, let's use our I. So we're going to do the I plus first term divided by the ith term, or times the reciprocal of the ith term. And then we know we gather the like things together, and we simplify, and we found this limit, right? And what is this whole big thing like, right? So let's not lose sight. This whole crazy expression boils down to what? What is that? Anybody know? Remember. Kenny.
So after doing all the things, you get -1. Excuse me.
I'm not asking about doing it. I'm asking about what is this? Why do we do this? What does this thing represent? Okay. And what is that? So yeah, ai plus 1. It's ai plus 1 over ai. Okay. But what's the idea of this? Why are we doing this? Anthony. Right. So what is this? This is the multiplier to get what? To the next term. And why do we care about that? It's the multiplier to get, so if we have this series, right, and we're adding all these things up, given any term, you would multiply by that, and it would give you the next term. So then what's the point? What is that about? Was it? That multiplier is like r in a geometric series, right? But r is constant, right? With a geometric series, that multiplier stays the same. So just now in any series, we can figure out what that multiplier is, and it can change from term to term, but we're seeing in the long run, what does that, we're taking the limit of this multiplier and seeing in the long run, does that converge on a number that we know a geometric series would converge, right? So if that multiplier turns out in the long run to be like between -1 and 1, then this is like that. Then the series is like turning into a geometric series with that r value. Okay, so that's an overview of why we do all this, right? So lots of algebra and exponents and symbols, but never lose sight of what the point is. We're seeing if it becomes like a geometric series that converges in the long run. Okay. So combine all the. So we're going to have a -1. We're going to have one more 19 in the bottom, is that right? We're going to have one more x minus 15 in the top. And then I'm going to have I squared over I plus 1 squared. And then I'm going to take the limit as I gets really big. And so as I gets really big, what does that thing do? It becomes like absolute value of x minus 15 over 19. Absolute value of -1 is just 1. And the limit of I squared over I plus 1 squared is a really easy limit. That's just 1. So we get this. And so as long as that limit is less than 1, then this thing is like becoming a geometric series that converges, right? So for whatever x values, makes our multiplier between -1 and 1, we'll make this series converge. All right, so we'll have x minus 15 over 19 between 1 and -1. So that means x minus 15 is less than 19 and greater than, so that's 15, -19. Are we good? Finally, x is going to be less than 34, greater than -4. Yes, sir?
So it's all the time. When you have the x minus 15 over 19, for any question where you kind of solve it as I gets infinitely bigger, when it's less than 1, that's when it converges.
It's the ratio test.
Right.
Ratio test always says, for the ratio test, if your limit of the multiplier, the absolute value of the multiplier is less than 1, then that's like the multiplier, that's like the R value becoming in the range that we know that converges for a geometric series. All right, so then all this question asks for is a radius of convergence. So let's just graph it here. So -4. So the radius doesn't have to do with whether the endpoints have convergence or not. We'll do that in a second. But let's just talk about the radius. So for -4 to 34, so we could first figure out what's the diameter, right? So you think like this is like a circle, and this is the diameter. What is that? 38. So then the radius is going to be half of that, 19, right? So we're going to go from, the center is 15, right? So look, the center is 15 right there. And so then we go 19 this way or 19 this way, and that gives us the whole interval. So the radius is going to be 19. Now what about the endpoints? So a valid question is, what about the endpoints? Does the series converge or not? So if we plug -4 in here, we'll get if we plug -4 in here, we'll get -19 to the n times -1 to the n over 19 to the n. We can combine that whole thing, and what does that whole thing become? Actually, +1, right? -19, -1, 19, all to the n. This is 1 to the n. So then we have 1 over n squared. Converge or not? P series, P is greater than 1. 1 over n squared. Converges. And that was what for, what I put in? -4? All right. Then I can put in +34. And what do I get? If I put in +34, this becomes +19 to the n. And now we combine all that stuff. What do we get? Yeah, these go away. So we get -1 to the n over n squared. Does it converge? Even better, right? Put the alternating on there just for good measure, right? We didn't need it, right? This converged absolutely, even without the -1 to the n, which we just saw when we plugged in -4. But now you've got -1 to the n over n squared also converges. So in this case, both endpoints are part of the interval. Sometimes it's one, sometimes it's neither, sometimes it's both. There's no guarantees.
If both points are part of the equation, does that necessarily imply that there is absolute convergence?
Maybe sometimes you see that. Yeah, so that's what happened here. I don't know about every time, but that's what happened here. That we have, because it's absolute convergence,
Okay.
whether you had the -1 to n or not. So I don't want to say it's a hard and fast rule, but it's a cool thing to keep in mind. Yeah. All right, any questions about this example? So then if you were asked for the interval, that would be the interval. -4 less than or equal to x, less than or equal to 34. These are the x values. Choose any x value in that range, put it in there, and you have a series that converges. If it's outside of that range, you get a series that doesn't converge. Diverges. Any questions? Okay, new topic. Well, new part to this topic. Oh, we have an exam on Friday. So all the review materials are up, and recitation this week, you'll just be practicing, answering questions about web work and doing. I've posted a lot of review questions. So web work will just be studying for the exam. Get started early. If the exams haven't gone, as well as you'd hoped, my number one piece of advice is get started studying early. Plan out lots of times to sit down and study, and then get your questions answered those last couple days before the test. Don't start even Wednesday night, or for sure not Thursday night. Okay? Yes, sir?
Is there any answer key to the problems on the exam prep that come back?
Maybe. I don't know how many odds I assigned. There might be odds. But, so definitely, with each other, working with each other, you can email me questions on particular ones. Come to office hours. We can work those out. And maybe, possibly I can post if there's the ones for the odds. Yeah. Other questions? Okay, so it'll be the same procedure as last time, which I forgot what that was. Do we come early? It's different with every class. We come at 9? Okay, we'll come here at 9 and go till 10:30, so you have 90 minutes. I think this exam is a little shorter though, so I think 90 minutes will be plenty. And then if that doesn't work for you, we'll make other arrangements, okay? Here we go. Okay, so Taylor and Maclaurin series. So a Taylor and Maclaurin series allows us to write any function, f. So what were power series like? They're like polynomials, right? So it's like an infinite polynomial. So what if you had a non-polynomial? Well, if you had a non-polynomial, like a cosine or sine or exponential function, log function, a Taylor and Maclaurin series allows you to take that non-polynomial and kind of fit a polynomial to it. Why would we want to do that? Well, if you think back to like derivatives and integrals, polynomial, that's like the easiest type of function to find derivatives and integrals of. They're just convenient functions, right? Polynomials, they're easy to work with. That's the sum of x to a power. And you just sum a bunch of those up. They're like really convenient functions. They're just based on pure arithmetic, right? They're just based on like multiplication and addition. So they're convenient functions to work with. So if you had something like cosine or an exponential function, you can use a Taylor and Maclaurin series to kind of figure out a polynomial that we can kind of fit to it or approximate with it. Okay? So how do we do that? So we say a Taylor polynomial centered at x equals a has this form. Okay, now don't let this scare you. This is just like polynomials, but there's one difference, right? All the x's have minus a. So we know polynomials are just a coefficient times x to the power plus coefficient times x to the power plus coefficient times x to the power. Not hard. So now here, it's the same thing, but all the x's are minus a. So what does that do? So what is just subtracting a from all your input values, or what does that do subtracting a? Like think about the graph. What does that do to the polynomial? What is it? Someone remembers? Shifts it to the right. Remember that? So it's just like taking a polynomial and just moving it a units to the right. And if a was negative, it would move it left, right? X minus negative would be plus, and then it would move it left. So this is just our basic polynomial with the possibility of taking that whole polynomial and shifting it over a, or shifting it a. Okay? So that's not bad. So given a function f, so f is our function that's not a polynomial, okay? That's the one we want to approximate with, say, t, a Taylor polynomial. So Taylor polynomial is we're going to kind of construct it to fit it on, or make it be like this given f function that we have. Does that make sense? So we're starting with a function f, and we're going to construct this Taylor polynomial to be like f, or try to approximate f, okay? And when we do that, we're going to center it. All right, so we're going to center it, and that's what the a is for. So it's going to be centered about x equals a. A is like the focal point of where we're going to try to fit this polynomial to the function. Okay, So all we need to find then are constructing this polynomial to fit f means finding the coefficients. So we're going to try. All we need to do is figure out what these coefficients are. If we can figure out what those coefficients are, then we can write this polynomial to try to approximate f, and that will be what we call centered about a. All right. So it's we'll see what that means in a second. Okay. So here we go. So at a. All right. So at a. What happens when you plug a into the Taylor polynomial? What do you get? No, you don't get 0. C0, right? C0. Okay, so if that's what we get when we plug a in, then what do we want C0 to be so that if we plug a into the function, we're going to get, so what do we want to happen at a? What do we want to happen at a? We want our polynomial, t of a, to do the best it can for the function at a. So then what is C0 going to be so that the polynomial gives us the function value at a, or does the best it can do centered at a? So what should C0 be? Does it make sense? So what should it be? So what should we assign to Z0? C0, so that when we plug a into our polynomial, we get the right function value, right? When we get the right function value. Any ideas? Yeah. Yeah, right. Maybe. Where are you? Oh, I guess I'm writing that. Yeah, so what we want to do is we want it to be f of a. See, because what would happen? If we make C0 f of a, right, f is the function we have, t is the one we're creating. So if we make C0 f of a, then what happens when you plug a into t? You're going to get f of a, and that's exactly what we want. So it would get the function value exactly right. The polynomial would get the function value exactly right at a. Doesn't that make sense? So then what we can do is to figure out what C1 is, we can take the derivative. Take the derivative of our polynomial, we get this, right? So we use the power rule, n times c to the n minus 1, and then n minus 1 to the n minus 2, all the way down to, when we take the derivative, the c naught goes away, and the last thing we have is C1. So then what's the first derivative at a of the polynomial? What is it? Not 0. Not 1. C1, right? C1. You plug a into this, all these go away except for 1C1. All right, so we have the function a, and we're trying to figure out what C1 should be, right? We have the function f. We have the function f. We're trying to figure out what should C1 be so that the function gets the derivative right at a. What should we make C1? What should we make C1 so that if you plug a into t prime, you get what? the first derivative correct. What should it be? Some people are saying it. F prime of A, right? That means make this coefficient the first derivative. And that makes sense, right? Because this is like mx, right? This is like the mx term, the linear term. The coefficient on the linear term is the first derivative, right? So far, if we plug a into our polynomial that we're constructing, if we plug a in, we get the function value right because we're assigning the function value to be c, this constant term, and we get the first derivative right because we have assigned the first derivative to be c1. All right, let's do it again. Take the derivative, second derivative. Okay, so now we do power rule again. So we get n times n minus 1 to the n minus 2. And then n minus 1 times n minus 2, and then the power to the n minus 3. We work our way all the way down, and now we get 2c2 as the constant term of the second derivative. The 1c1 goes away, and we get 2c2. So that means the second derivative at a is 2 times 1 times c2. And we want that to get the second derivative right. So that forces it to get the second derivative right. So therefore, what are we going to make c2 so that our polynomial, the polynomial we're making gets the second derivative right? What are we going to make c2? Is that what c2 is going to be? F double prime? Yeah, so we got to, so now in order for c2 to be, for this t, the second derivative at a to be correct, c2 would have to be f double prime what? Divided by 2. I'm going to write 2 times 1. Do it one more time. Don't do that. Okay, third derivative. Take the third derivative. It's the derivative of the second derivative. So if you want to copy that down, do it from the video. Don't listen for now. So in the end, we get down to, this is the last term that stays around. 3 times 2 times 1 c3. That one, the derivative is 0 because it's constant. Okay, so then our third derivative at a is 3 times 2 times 1 c3. And we want to get the third derivative right, so we're going to assign that to third derivative at a, which tells us what does c3 need to be? Right. So what does c3 need to be so that this is true, that we get the third derivative in our polynomial right for the function? So c3 should be triple prime. And what is that? 3 times 2 times 1. Yeah, but 3 factorial. And this was 2 factorial. And this can be thought of as? And 0 factorial, which is 1. Right? That's one way to think of it. There's other ways too. Okay, so what are we doing? We've got this function f, and we want to model it by this t function. We want to model it with this polynomial, so we said we need the coefficients. So by looking at the function at a, we could get the function right at a by making the constant f of a. And then we said we could make it the first derivative right at a By making the C1 coefficient f of a, or f prime of a, divided by 1 factorial. And we said we could get the second derivative right? So it's t double prime at a equals to f double prime of a, if we make that coefficient f double prime a over 2 factorial, and etc. So we saw that, and then the same thing with the third derivative. If we force our polynomial to get the third derivative right, that would mean C3 would have to be f triple prime of a over 3 times 2 times 1, or 3 factorial. So what are we doing? We're building this polynomial so that it keeps getting everything right at a. And the more stuff that we get right at a, the more derivatives we get right at a, the better it's going to approximate our function near a. We're going to see it. I'll show you in the graph. Okay. So again, the more things we get right at a, the better our t function will approximate f near a. Okay, so what about the nth? So if I go up to the nth, I want to get the nth coefficient, and so if I want to get the nth derivative right at a, what do you think the nth derivative will be if we were keep taking derivatives? The nth derivative would be what? What will it be? N factorials, and then the coefficient, right? And then if we wanted to get the nth factorial correct, we want to get the nth derivative, if we want to get the nth derivative of f correct, that means that the nth coefficient should be what? So this is the general term for all the coefficients. Cn would be nth derivative over n factorial. So the nth derivative over n factorial is the key for all the that's what we want to make all the coefficients in order for that polynomial to reproduce our function. Okay, but then that's going to have it's just going to be approximate. So we'll see this in a second. Okay, anybody have a question? So again, constructing a polynomial means figuring out what the coefficients need to be so that it's getting as much right as possible for f at a. That's what this was all based on. That was our final conclusion here. So let's look at an example and some graphs. So here is sine of 1/2 of x. So I want you to, based on what we just talked about, I want you to find those coefficients, C0 through C4, so C0, C1, C2, C3, C4. And then find the Taylor polynomials. T0 through T4. So T4 will be, we'll have all the terms up to and including the fourth degree, right? So this is a 4th degree polynomial. It'll have all the lower degree terms as well. So first I want you for this function sine of 1/2 x. So what's going to be our goal? We want to reproduce sine of 1/2 x, and we want our center to be 1, meaning our focal point is going to be right here at 1. So first to do that, we're going to find the Taylor coefficients. Like I said, C0, C1, C2, C3, C4. Once you have those, then you can write a series of polynomials. Each polynomial will include all the terms from before. Okay, so the 4th degree polynomial, the last one that you write, will have all the terms. It'll have terms of all degree up to degree 4. Okay, so work together. Morteza and Pollock are here to help you, and you work together. So you're using what we found, applying it to this example. Okay, you're either making progress or you're getting help. You're making progress or you're getting help. Sine of 1/2 times what do you think? What did you say? First of all, what did you say? So sine 1/2 x. But we didn't say it was equal to the full function, but the function evaluated at a, right? So it'd be sine 1/2 of, or sine of 1/2.
That makes a lot of sense.
So C naught was just in general, it was f of a, right? F of a. Is that right? So C naught is sine of 1/2. Anybody?
C0?
Yeah.
Yeah, C1 1/2 cosine.
Not cosine. So f is sine of 1/2 x, and C naught is f of a. So what is that? Sine of 1/2. I'm gonna die. You guys, what's f of a? What's f of a? If f of x is sine of 1/2 x, then f of a is sine of 1/2 times a, or 1, right? In this case, it's 1, but we could just write a. F of a, guys, f of a, right? Function notation. Function notation. If f of x is sine of 1/2 x, then f of a is sine of 1/2 a. In this case, a is 1, so we could plug a in for 1, but I'm going to just keep the a's for us, okay? All right, so C1 is what?
1/2 cosine of 1/2.
F prime of a, right? Or over 1 factorial if you want, but f prime of a. So that's going to be 1/2, right? Times cosine of. In our case, it's 1, right? What's C2? Negative. So the second derivative would be negative a fourth.
Sine, and then the argument right there.
Good. All over 2 factorial, or 2. Let's jump to the 4th derivative. What's the 4th derivative going to be? How many 0.5s will we have in front now? Won't we have 4 by now? Will it be negative or positive? Positive, because we get cosine, and it'll be negative cosine here, and then it'll be positive sine. Sine of 1/2 a, or 4 factorial. Okay, so then what is T4? So T4, and you just add the so there's, just add the coefficients. So those are coefficients, meaning they're multiplied by something, right? So we'll just skip to the T4th. So it'll be yeah, so let's do it that way, so we don't have to write it all out. So we already wrote what C4 was, so it'll be C4 times x to the fourth, x minus a to the fourth. So I'll put the ones in now. So it'll be x minus 1 to the fourth. Then what we got for C3, and then let's do that quickly. C3 should have been 0.5 cubed cosine 0.5a all over. That should have been your C3. So it'll be C3 times x minus 1 cubed plus but now we know these coefficients because we had the function. So with the function, we built the coefficients. And then with the coefficients, we can build the polynomial, the fourth degree polynomial that approximates f. So the best part is about to come. Don't tune out. This is the best part coming up here. So first of all, questions about finding the c's or then using those c's to write. All I did was T4. I didn't write out. In fact, I have the other ones written out below. I'll show you them in a second. But any questions about finding the c's or writing out the fourth degree polynomial? Yes, please. Yeah, so it wouldn't. You could, but it wouldn't be like it wouldn't make sense to take a polynomial and try to approximate it with a polynomial because it already is a polynomial. Exactly. So it's all. So these non-polynomials have, right? These non-polynomial functions have like an unlimited number of derivatives, so you can keep going. Exactly. Yep. Other questions? Okay, so let's see how this thing plays out. So what did we say? The t0th polynomial would just be C0. What does that get right? What does that get right? So let's take a look here. So here's the polynomials, or here's the coefficients. Did I write out the polynomials? I did. So here's the, this is the 0th polynomial. It's just, all it is the constant term. So what does it get right? The only things it gets right is what? It's trying to approximate, so this is, it's a polynomial that's trying to approximate the red graph, the f, the sine of 1/2 graph. And we force the coefficient to be what? So that we get what right about the function? No, what about the function does this C0 get right? Just the function value. So what does that look like? All it does is get the function value right at 1. See that? It'll just end up being the graph 1/2. The t0th polynomial just ends up being the graph of y equals 1/2. And why is that significant? No, not, is it? Yeah, 1/2. Because that's what you get when you plug 1 into the function. So the only thing this blue graph is getting right as it tries to approximate the red graph, it just gets the function value right at 1, just that 1 point. See that? So now what about T1? The first, or this, the next polynomial. C0 plus C1 x minus a. What does that get right? So that's the first degree polynomial. It gets the function value right, but it also gets one other thing right. What else does it get right? We're creating polynomials that are trying to reproduce the red graph, right? And we did that by what? By taking derivatives and trying to get what? We got the function value right with the first coefficient, and the second coefficient, what did it get right? The rate of change. So what do you expect this to look like? Good. Someone got it. Tangent line, right? So now this is T1 polynomial. It gets the function value right, but it also gets the first derivative right. So now you see around 1, it's starting to approximate the function. All right, what about the third, or the second degree polynomial? That's going to get the function value right, and the first derivative right, and the second derivative right. That's the way we forced it, right? We forced it to do that. So what does that look like? It's going to be a quadratic that gets the function value right and the first two derivatives right. And so now you see it's starting to do a good job around 1, centered at 1. All right, next, the T3 polynomial. It gets the third derivative and all previous derivatives right and the function value. So now, look, it's starting to really match the function really well, close to 1, but for wider and wider. Sorry. Okay, last one. So this is the one that we wrote out. This is the fourth degree polynomial. That's this one. It gets the fourth derivative right, the third, the second, the first derivative, and the function value right. And so the more derivatives you get right, the wider the interval, it does a good job approximating around the center.